What if the key to unlocking the secrets of the universe lies in a cosmic short, cut so small you could miss it? Imagine being able to step through a doorway that could take you to the farthest corners of the galaxy, or even to a different time entirely. This isn't just science fiction, it's the mind-bending reality of wormholes and space-time travel. Today, we're diving into 50 astonishing theories that explore how these mysterious tunnels in the fabric of the cosmos might work. From the brilliant minds of Einstein and Thorne to cutting-edge quantum physics, we'll unravel the possibilities that could redefine our understanding of space, time, and existence itself. So, are you ready to embark on a journey through the unknown? Let's step into the world of wormholes and discover what lies beyond the limits of our imagination. Now, let's turn our attention to the very foundation of wormhole theory. The idea of wormholes first emerged from the brilliant minds of Albert Einstein and Nathan-Rosen back in the 1930s. They proposed something extraordinary: bridges through space-time that could connect two distant points in the universe. These structures, now known as Einstein-Rosen bridges, were born out of Einstein's theory of general relativity. At their core, these bridges are solutions to the equations that describe how gravity warps space-time. Picture space-time as a vast, flexible sheet. If you could fold that sheet, an Einstein-Rosen bridge would act as a tunnel connecting two distant points, effectively creating a shortcut through the cosmos. But here's the catch: these bridges aren't exactly the traversable wormholes we see in science fiction. They're more like cosmic shortcuts that are incredibly unstable. In fact, they would collapse almost instantly under their own gravitational pull, making them impossible to pass through. Despite this, Einstein and Rosen's work laid the groundwork for all future wormhole theories, showing us that the fabric of space-time might have hidden pathways waiting to be discovered. This theory not only expanded our understanding of general relativity, but also opened the door to endless possibilities in physics. It's a testament to how even the most abstract ideas can reshape our view of the universe. Next, we'll explore how modern physicists have built on this foundation to imagine wormholes that might actually be traversable. Building on Einstein and Rosen's groundbreaking work, let's take a step into the modern era of wormhole theory. Physicists Kip Thorne and Michael Morris took the idea of space-time bridges and asked a crucial question: could these structures ever become stable enough to traverse? Their work led to what we now call Morris-Thorne wormholes, a concept that brings us closer to the kind of wormholes we see in science fiction. Unlike Einstein-Rosen bridges, which are inherently unstable and would collapse instantly, Morris-Thorne wormholes are designed to remain open and potentially passable. But here's the twist: keeping a wormhole stable requires something truly extraordinary: exotic matter. This isn't the kind of matter we're familiar with in our everyday lives. Exotic matter would need to possess negative energy or negative mass, which would counteract the immense gravitational forces trying to crush the wormhole shut. Think of it like using an invisible support beam to hold open a tunnel through space-time. Without this exotic matter, a Morris-Thorne wormhole would collapse just as quickly as an Einstein-Rosen bridge. While exotic matter remains purely theoretical, its inclusion in the Morris-Thorne model opens up fascinating possibilities. It suggests that, under the right conditions, wormholes could become viable shortcuts through the cosmos, bridges not just in space but potentially in time as well. This modern interpretation of wormholes has inspired countless scientific explorations and even fueled ideas in popular culture. Next, we'll venture into another intriguing possibility. What if wormholes could lead us to the mysterious counterparts of black holes, white holes? Now, let's shift our focus to an idea that feels almost like science fiction but is firmly rooted in theoretical physics: the possibility that wormholes could be linked to white holes. If black holes are known for pulling everything in, white holes are their polar opposites, objects that would theoretically expel matter and energy rather than trapping them. While black holes have been observed and studied, white holes remain entirely speculative, existing more as mathematical solutions to Einstein's equations than as confirmed cosmic phenomena. But here's where it gets interesting. Some theories suggest that white holes could serve as the exit point for a wormhole, creating a one-way tunnel through space-time. Imagine traveling through a wormhole and emerging from a white hole in a completely different corner of the universe or even a different time. This idea ties the two concepts together in a way that feels elegant but raises plenty of questions. For instance, if white holes exist, why haven't we detected them? One possibility is that they are incredibly rare or short-lived, only appearing under specific conditions. Another is that they are hidden in regions of space we haven't yet explored. While the connection between wormholes and white holes is still highly speculative, it's a fascinating concept that challenges our understanding of the cosmos and opens up new avenues for exploration. Next, we'll explore how wormholes might not just connect distant points in space, but could also bend the very fabric of time itself. Taking a step further into the realm of the extraordinary, let's consider how wormholes might not only bridge vast distances in space, but also manipulate time itself. The idea of traveling through time has fascinated humanity for centuries, and wormholes could offer a theoretical pathway to make it possible. According to Einstein's theory of general relativity, time dilation occurs when gravity warps space-time. This means that time passes differently depending on where you are in the universe. A wormhole as a tunnel through space-time could potentially magnify this effect. Imagine entering one end of a wormhole and emerging at the other end, not just in a different location, but also in a different time, either in the past or the future. This concept is tied to the idea of closed time-like curves, which are paths through space-time that loop back on themselves, allowing for the possibility of time travel. However, this raises some mind-bending paradoxes. For instance, what would happen if you traveled back in time and prevented your own birth? These paradoxes, like the famous grandfather paradox, challenge our understanding of cause and effect. While the math behind wormholes and time travel is intriguing, it also suggests that such journeys might be impossible without violating the laws of physics. Yet, the idea remains a captivating topic for scientists and storytellers alike, pushing the boundaries of our imagination and our quest to understand the universe. Next, we'll explore how the strange phenomenon of quantum entanglement might be linked to wormholes, opening up even more mysteries about the fabric of reality. Now, shifting our focus to the quantum realm, let's explore a fascinating idea that connects the strange world of quantum entanglement with the concept of wormholes. This connection is rooted in what's known as the ER=EPR conjecture, a theory proposed by physicists Juan Maldaisner and Leonard Susskind. At its core, this idea suggests that quantum entanglement, the phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter the distance, might actually be mediated by microscopic wormholes. Imagine these wormholes as tiny bridges between entangled particles, creating a hidden connection through space-time. This theory challenges our traditional understanding of both quantum mechanics and general relativity, suggesting that the fabric of reality might be far more interconnected than we ever imagined. If true, it could mean that wormholes aren't just cosmic shortcuts for travelers, but fundamental features of the universe itself, woven into the very structure of space-time. While this idea is still speculative, it opens up exciting possibilities for unifying the laws of physics, offering a potential bridge between the microscopic world of particles and the vast cosmos. As we continue to unravel these mysteries, the connection between quantum entanglement and wormholes reminds us that the universe is full of surprises waiting to be discovered. Next, we'll dive into how string theory incorporates wormholes, exploring the idea of higher dimensional spaces and their role in the cosmos. Turning our attention to the realm of string theory, we find another intriguing perspective on wormholes. String theory proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings exist in higher dimensional spaces, beyond the familiar 3 dimensions of space and 1 of time. Within this framework, wormholes could emerge as natural features of these higher dimensions, offering shortcuts through the fabric of the cosmos. Imagine the universe as a vast, multi-layered structure, with wormholes acting as tunnels connecting different layers. This idea suggests that the universe might be far more complex and interconnected than we perceive in our everyday experience. While these higher dimensions remain theoretical, they provide a compelling explanation for how wormholes could exist and function. By exploring these possibilities, string theory not only expands our understanding of wormholes, but also challenges us to rethink the very nature of reality. As we venture further into these ideas, we'll next examine how wormholes could serve as cosmic shortcuts, bridging unimaginable distances in space. Taking a step further into the realm of cosmic possibilities, let's consider wormholes as shortcuts through the vastness of space. Imagine trying to travel from one end of the galaxy to the other, a journey that could take millions of years at the speed of light. Wormholes could offer a solution, acting as bridges that drastically reduce the distance between 2 points. Think of it like folding a piece of paper so that the 2 ends touch, allowing you to jump from one side to the other in an instant. This concept isn't just science fiction. It's grounded in the mathematics of general relativity, which suggests that space-time can be warped in ways that create these tunnels. For interstellar travel, this could mean reaching distant stars or galaxies in a fraction of the time. However, there are significant challenges. Wormholes would require exotic matter to stay open, and their stability is still a major question. Plus, navigating through them could be incredibly risky, with the possibility of extreme tidal forces or even collapse mid-journey. Despite these hurdles, the idea of wormholes as cosmic shortcuts opens up exciting possibilities for exploring the universe. It challenges us to think beyond conventional limits and imagine a future where the stars might be closer than they seem. Shifting our perspective to an even grander scale, let's explore the idea that wormholes might not just link distant points in space-time but could also connect entirely different universes. This brings us to the concept of the multiverse, a fascinating theory suggesting that our universe is just one of many, each with its own unique laws of physics and dimensions. Imagine wormholes as gateways between these parallel realities, offering a passage from one universe to another. The multiverse theory, while still speculative, is supported by various interpretations of quantum mechanics and string theory. Wormholes could serve as the cosmic bridges that make such interdimensional travel possible, though the challenges are immense. The energy required to create and stabilize such a passage would be beyond anything we currently understand, and the physical laws governing other universes might be completely alien to us. Yet the possibility is tantalizing. What if wormholes could allow us to glimpse or even visit realities where history unfolded differently, or where the fundamental forces of nature operate in ways we can't yet imagine? This theory not only expands the scope of wormhole science, but also invites us to rethink the very nature of reality itself. It's a compelling reminder that the universe, or perhaps the multiverse, is far more complex and mysterious than we've ever imagined. Taking our exploration even further, let's consider the intriguing relationship between wormholes and one of the most elusive forces in the universe, dark energy. This mysterious force, believed to be responsible for the accelerated expansion of the universe, might also play a crucial role in stabilizing wormholes. Ordinarily, wormholes are thought to collapse under their own gravitational pull almost instantly, making them impossible to traverse. However, dark energy with its repulsive effect could counteract this collapse. The idea is that dark energy's expansive nature could provide the necessary pressure to keep a wormhole open, acting as a sort of cosmic counterbalance to gravity. This raises an exciting possibility. If we could somehow harness or manipulate dark energy, we might be able to create stable, traversable wormholes. Of course, this remains speculative, as dark energy itself is still poorly understood. We don't yet know how to interact with it or control it, but the potential is fascinating. Imagine dark energy as the key to unlocking wormholes, transforming them from theoretical curiosities into practical pathways through space and time. This theory not only deepens our understanding of wormholes, but also highlights the interconnectedness of the universe's most enigmatic phenomena, reminding us just how much there is left to discover. Now, let's shift our focus to another fascinating connection in the world of physics: wormholes and quantum tunneling. Quantum tunneling is a phenomenon where particles seem to tunnel through barriers that, according to classical physics, should be impossible to pass. Think of it like a ball rolling up a hill and suddenly appearing on the other side without ever reaching the top. At the quantum level, particles don't follow the straightforward rules we're used to. Instead, they can appear on the other side of a barrier because of their wave-like nature and the inherent uncertainty of quantum mechanics. Now, how does this relate to wormholes? Some scientists have drawn an intriguing analogy between the two. Just as particles can tunnel through barriers, it's theorized that wormholes might act as cosmic tunnels, allowing objects to traverse immense distances in space-time without physically crossing the space in between. While quantum tunneling happens on a microscopic scale, wormholes could be the macroscopic version, bridges that connect distant points in the universe. Of course, scaling up from particles to starships is no small leap. The energy and conditions required for such a process are still far beyond our understanding. But the idea opens up a compelling parallel. If particles can bypass barriers, perhaps wormholes could allow us to bypass the vast expanses of space. This theory not only bridges two seemingly unrelated concepts, but also inspires us to think creatively about the possibilities of the universe. Moving deeper into the mysteries of space, let's explore the intriguing possibility that wormholes might exist within the interiors of black holes. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. But what lies beyond this boundary? Some scientists speculate that the interiors of black holes could conceal wormholes, gateways that connect distant regions of space or even different universes. This idea stems from the equations of general relativity, which suggest that the intense gravitational forces inside a black hole could warp space-time in such a way as to create a tunnel-like structure. However, exploring this theory is no easy task. The conditions inside a black hole are so extreme that our current understanding of physics breaks down. For instance, matter is compressed to infinite density at the singularity, and the laws of quantum mechanics and general relativity clash in ways we can't yet resolve. Additionally, the event horizon acts as a one-way barrier, making it impossible to send information or probes inside and retrieve data. Despite these challenges, the idea of black holes harboring wormholes continues to captivate researchers. It raises profound questions about the nature of space, time, and the universe itself. Could these cosmic giants be holding the keys to interstellar travel or even the multiverse? While the answers remain elusive, the speculation itself pushes the boundaries of our imagination and inspires us to keep exploring the unknown. Shifting our focus to another groundbreaking theory, let's examine how wormholes might intersect with the phenomenon of Hawking radiation. This concept, introduced by the legendary physicist Stephen Hawking, revolutionized our understanding of black holes. Hawking proposed that black holes aren't completely black. They emit a faint radiation due to quantum effects near the event horizon. This radiation causes black holes to slowly lose mass and, over immense timescales, evaporate entirely. But what does this have to do with wormholes? Some researchers speculate that the same quantum processes responsible for Hawking radiation could also influence the behavior of wormholes. If wormholes are connected to black holes, as some theories suggest, the radiation emitted by black holes might affect the stability of these cosmic tunnels. For instance, the energy loss from Hawking radiation could destabilize a wormhole, causing it to collapse. On the other hand, others hypothesize that the radiation might provide a mechanism to keep wormholes open, acting as a counterbalance to the intense gravitational forces trying to close them. The interplay between Hawking radiation and wormholes remains a topic of intense debate. It raises fascinating questions about the relationship between quantum mechanics and general relativity, two pillars of modern physics that don't always play nicely together. Could Hawking radiation be the key to unlocking the secrets of wormholes, or does it present yet another obstacle to their existence? While the answers are still shrouded in mystery, the exploration of this connection continues to inspire physicists to rethink the boundaries of our universe. Now, let's journey back in time to the very beginning of the universe and explore an intriguing theory. Could wormholes be remnants of the Big Bang? The Big Bang, the explosive event that gave birth to our universe, created a chaotic and dense environment where the laws of physics as we know them were stretched to their limits. In this primordial soup of energy and matter, some researchers propose that wormholes might have formed as natural features of space-time. These early wormholes could have been tiny, quantum-sized tunnels, potentially acting as bridges between different regions of the rapidly expanding universe. But why would they have formed during the Big Bang? The intense energy and curvature of space-time in those first moments could have allowed for the spontaneous creation of these exotic structures. If they did form, what would that mean for cosmology? Some scientists suggest that these ancient wormholes could still exist today, hidden relics of the universe's infancy. They might persist as microscopic tunnels, perhaps even connecting distant parts of the cosmos in ways we're only beginning to understand. Additionally, the presence of wormholes from the Big Bang could offer clues about the universe's early conditions and the nature of space-time itself. For instance, if we could detect signs of these primordial wormholes, it might help us unravel some of the mysteries surrounding the universe's origins and evolution. This theory also raises profound questions about the fabric of reality. Could these wormholes have influenced the large-scale structure of the universe we see today? Or might they still play a role in the cosmic dance of galaxies and dark matter? While the idea of wormholes as Big Bang remnants remains speculative, it's an exciting area of research that continues to push the boundaries of our understanding. By studying these potential time capsules from the dawn of the universe, we might unlock new insights into the cosmos and our place within it. Now, let's shift our focus to a fascinating intersection of physics and philosophy, the holographic principle and its intriguing connection to wormholes. The holographic principle suggests that all the information about our three-dimensional universe could be encoded on a two-dimensional surface, much like a hologram. This idea challenges our traditional understanding of space and reality, proposing that what we perceive as a three-dimensional world might actually be a projection from a lower dimensional plane. So, how do wormholes fit into this picture? Some theories propose that wormholes could serve as conduits or bridges, facilitating the transfer of information between these dimensions. Imagine a wormhole acting as a kind of cosmic tunnel, linking the holographic boundary where all the universe's information is stored to the three-dimensional space we inhabit. This concept could revolutionize our understanding of information flow in the cosmos. For instance, if wormholes are indeed involved in this process, they might play a crucial role in how the universe encodes, processes, and retrieves information. This idea also raises profound questions about the nature of reality itself. Could wormholes be the mechanisms that allow the holographic principle to function, connecting the lower dimensional code to the higher dimensional reality we experience? While this theory is still in its speculative stages, It opens up exciting possibilities for exploring deeper connections between wormholes, space-time, and the very fabric of the universe. By studying these ideas, we might uncover new insights into how information is structured and preserved in the cosmos, potentially bridging the gap between quantum mechanics and general relativity in ways we've never imagined. Now, let's dive into a groundbreaking idea that could change the way we detect wormholes' gravitational waves. These ripples in the fabric of space-time, first predicted by Einstein and later observed by scientists, have opened up a new window into the cosmos. Gravitational waves are created by massive cosmic events like the collision of black holes or neutron stars, sending shock waves through space-time itself. But could these waves also hold clues to the existence of wormholes? Some researchers believe that wormholes, if they exist, might produce unique gravitational wave signatures. Imagine a wormhole as a tunnel connecting two distant points in space. If something were to pass through it, perhaps a star or even another black hole, the resulting disturbance could generate gravitational waves unlike anything we've seen before. These waves might carry distinct patterns or frequencies, acting as a cosmic fingerprint for wormholes. Detecting such signals would not only confirm the existence of these mysterious structures, but also give us a way to study their properties. For instance, we could potentially measure their size, stability, and even the exotic matter required to keep them open. While this remains speculative, the idea is incredibly exciting for both physicists and astronomers. By analyzing gravitational wave data, we might uncover evidence of wormholes lurking in the universe, hidden in plain sight. This approach could revolutionize our understanding of space-time, connecting theoretical physics with real-world observations. As we continue to refine our detection methods, the search for wormholes through gravitational waves could become one of the most thrilling scientific endeavors of our time. Moving forward, let's explore one of the most debated concepts in wormhole theory, whether these cosmic tunnels could enable faster-than-light travel. The idea of traveling faster than light has long been a staple of science fiction, but could wormholes make it a reality? According to some theories, a wormhole could act as a shortcut through space-time, allowing something to travel immense distances almost instantaneously. While this doesn't technically mean moving faster than light, it could achieve the same outcome by bending the rules of space and time. Imagine a wormhole connecting Earth to a distant star system thousands of light years away. Passing through the wormhole could take mere seconds, even though the journey would take millennia if traveled through conventional space. This raises fascinating questions about the nature of speed, distance, and time itself. However, the implications for physics are profound. Einstein's theory of relativity states that nothing can travel faster than light, as it would require infinite energy. Wormholes, if they exist, might offer a loophole in this rule, but not without challenges. For one, the stability of wormholes would require exotic matter or negative energy, which we've yet to discover. Additionally, the very act of traversing a wormhole could have unpredictable effects on causality, potentially leading to paradoxes. Despite these hurdles, the potential for interstellar exploration is tantalizing. If wormholes could indeed provide faster-than-light travel, they might open up the universe to humanity in ways we've only dreamed of. Distant star systems, once thought unreachable, could become within our grasp. While this remains speculative, the idea continues to inspire scientists and dreamers alike, pushing the boundaries of what we believe is possible. As we continue to explore the mysteries of wormholes, the question of faster-than-light travel remains one of the most intriguing possibilities in the cosmos. Now, let's shift our focus to another mind-bending possibility. Could wormholes connect not just different points in space-time, but entirely different universes? The idea of parallel universes has fascinated scientists and fiction writers alike, suggesting that our universe might be just one of countless others, each with its own unique set of physical laws and possibilities. Wormholes could, in theory, act as bridges between these parallel realities. The concept of multiverse theory, which proposes the existence of multiple or even infinite universes, gains an intriguing layer when combined with wormhole physics. If wormholes can connect distant points in our universe, why couldn't they extend their reach to other universes entirely? This idea draws on the mathematical framework of string theory, which suggests higher dimensional spaces where such connections might be possible. Imagine stepping through a wormhole and emerging in a universe where the laws of physics are entirely different, where time flows backward, or gravity behaves in unexpected ways. While this remains speculative, the implications are staggering. Wormholes could offer a way to explore these alternate realities, or even serve as pathways for information or energy to travel between universes. However, the challenges are immense. Traversing such a wormhole would require overcoming not just the instability of the wormhole itself, but also the potential for entirely unknown conditions on the other side. Additionally, the very concept of parallel universes raises questions about causality and identity. Would the you in another universe even be the same person? Despite these uncertainties, the idea of wormholes as bridges to parallel universes continues to inspire both scientific inquiry and creative imagination, pushing us to rethink the boundaries of reality itself. Shifting gears, let's explore an equally fascinating concept: wormholes and their potential to create closed time-like curves, effectively forming time loops. Imagine a scenario where traveling through a wormhole could bring you back to a point in your own past, creating a loop in time. This idea, rooted in the mathematics of general relativity, suggests that wormholes could allow for events to repeat endlessly, blurring the line between cause and effect. One of the most famous paradoxes this raises is the grandfather paradox. What if you went back in time and altered an event that prevented your own existence? Such paradoxes challenge our understanding of causality and free will, forcing us to reconsider the nature of time itself. Physicists have proposed various solutions, like the idea of self-consistent timelines, where any changes made in the past are already part of the loop, ensuring consistency. Another intriguing possibility is the concept of branching timelines, where each journey through a wormhole creates a new alternate reality, sidestepping paradoxes but introducing a multiverse-like scenario. These time loops also raise philosophical questions about identity and continuity. Would the you at the end of the loop still be the same person who started it? While these ideas remain speculative, they push the boundaries of both physics and philosophy, offering a glimpse into how wormholes might not just connect space, but also twist and fold time in ways we're only beginning to comprehend. As we ponder these possibilities, the implications for our understanding of the universe and our place within it become both thrilling and profoundly unsettling. Building on the mind-bending concepts of time loops, let's now turn our attention to an equally profound idea: wormholes as natural features of the fabric of space-time. Think of space-time as a vast, stretchable sheet, with massive objects like stars and planets creating dips and curves in its surface. Wormholes, in this view, could be natural wrinkles or tunnels within this fabric, formed by the intense gravitational forces that warp space-time itself. Some theories suggest that wormholes might have emerged in the early universe during the extreme conditions of the Big Bang, when space-time was highly dynamic and fluctuating. Others propose that they could form in regions where space-time is stretched to its limits, such as near black holes or during cosmic collisions. What's fascinating is that these structures might not be rare anomalies, but rather fundamental aspects of the universe's architecture. If wormholes are indeed natural features, they could provide clues about the underlying nature of space-time itself, perhaps revealing that it's not as smooth and continuous as we once thought, but instead filled with intricate, interconnected tunnels. This idea also aligns with some quantum gravity theories, which suggest that space-time might have a granular, foamy texture at the smallest scales, where wormholes could naturally exist. By studying wormholes, we might uncover deeper truths about how space-time works, shedding light on the very fabric of reality. As we explore this theory, it's clear that wormholes are not just shortcuts through space, they might be windows into the fundamental structure of the universe itself. Shifting our gaze beyond our own understanding of wormholes, let's consider the possibility that advanced alien civilizations might already be using these cosmic tunnels for interstellar travel. Imagine a civilization far more technologically advanced than ours, one that has mastered the complexities of traversing wormholes. For them, these space-time shortcuts could be the highways of their galaxy, allowing them to move between star systems in the blink of an eye. If such civilizations exist, wormholes might be the key to their ability to explore, colonize, or even monitor distant worlds, including our own. This idea raises intriguing questions for the search for extraterrestrial intelligence or SETI. If alien civilizations are using wormholes, could we detect their presence through the gravitational signatures or energy emissions these structures might produce? Or perhaps wormholes could serve as communication channels, enabling civilizations to send signals across vast distances instantly, bypassing the limitations of light-speed travel. The existence of wormholes could also explain why we haven't found concrete evidence of extraterrestrial life, yet maybe they're traveling and communicating in ways we're only beginning to comprehend. If we ever discover a wormhole, it might not just be a gateway to another part of the universe, it could be a sign that we're not alone. Exploring this theory challenges us to think bigger, pushing the boundaries of our search for life beyond Earth. Next, we'll dive into the intriguing connection between wormholes and the Anthropic principle, exploring how the existence of these structures might be tied to the very fabric of our universe. Turning our attention to the broader implications of wormholes, let's consider their connection to the Anthropic principle. This principle suggests that the universe's fundamental constants and laws appear finely tuned to allow for the existence of life. Could wormholes be part of this cosmic fine-tuning? If so, their existence might not be a mere coincidence, but rather a necessary feature of a universe capable of supporting intelligent beings. The Anthropic principle invites us to ask why the universe is the way it is. Why do the laws of physics allow for structures like wormholes? One possibility is that wormholes play a role in shaping the universe's large-scale structure, creating pathways that enable the distribution of matter and energy in ways that support the development of life. Alternatively, wormholes might be essential for advanced civilizations to thrive, serving as tools for exploration and communication across vast cosmic distances. If the universe is indeed fine-tuned for life, then the existence of wormholes could be a byproduct of this tuning, designed to unlock new possibilities for discovery and connection. This idea pushes us to think about the universe not just as a random collection of particles and forces, but as a carefully balanced system that might have a purpose or direction. Exploring this theory raises fascinating questions about the nature of our cosmos and our place within it. Next, we'll delve into the mysterious role of vacuum energy in stabilizing wormholes and what this could mean for their potential use in space-time travel. Now, shifting our focus to the role of vacuum energy in the realm of wormholes, we encounter a concept as intriguing as it is complex. Vacuum energy, often referred to as the energy of empty space, plays a crucial part in the stability of these cosmic tunnels. Imagine the vacuum of space not as a void, but as a seething sea of energy fluctuations. These tiny ripples in the fabric of space-time could be key to keeping wormholes open, counteracting the immense gravitational forces that would otherwise cause them to collapse. However, harnessing vacuum energy is no simple feat. It requires exotic matter with negative energy density, a theoretical substance that defies our everyday understanding of physics. The challenge lies in both creating and controlling such matter, as well as understanding how it interacts with the vacuum energy itself. If successful, this could pave the way for traversable wormholes, enabling travel across vast distances in space. Yet the practical hurdles are immense. Vacuum energy is notoriously difficult to manipulate, and the exotic matter needed remains purely speculative. This theory pushes the boundaries of our current knowledge, inviting us to explore the profound connection between the energy of empty space and the stability of wormholes. Next, we'll explore how the Casimir effect might offer another avenue for stabilizing these cosmic shortcuts. Moving forward, let's examine the Casimir effect and its fascinating potential to stabilize wormholes. The Casimir effect is a quantum phenomenon where two uncharged parallel metal plates placed extremely close together experience an attractive force. This force arises from the quantum fluctuations in the vacuum of space itself, creating a subtle but measurable pressure between the plates. Now, imagine harnessing this effect on a cosmic scale. Some physicists speculate that the Casimir effect could provide a mechanism to counteract the immense gravitational forces that threaten to collapse wormholes. By leveraging the energy from these quantum fluctuations, it might be possible to create a stabilizing force that keeps the wormhole's throat open. However, the challenge lies in scaling this effect to the size of a wormhole, which would require an extraordinary amount of energy and precision. Additionally, the exotic matter needed to maintain such stabilization remains a theoretical concept. Despite these hurdles, the Casimir effect offers a tantalizing glimpse into how the strange behaviors of quantum physics might intersect with the vast structures of general relativity. As we continue to explore this idea, we're reminded of the intricate and often unexpected connections between the microscopic and the cosmic. Next, we'll turn our attention to how wormholes might play a role in resolving the black hole information paradox. Now, let's shift gears to explore one of the most perplexing mysteries in modern physics, the black hole information paradox, and how wormholes might hold the key to solving it. The paradox stems from a fundamental conflict between quantum mechanics and general relativity. According to quantum mechanics, information about the state of a system can never be destroyed. Yet, when matter falls into a black hole, it seemingly vanishes along with all the information it carries. This contradiction has puzzled physicists for decades. Enter wormholes. Some theories suggest that wormholes could provide a hidden pathway for information to escape a black hole. Instead of being lost forever, the information might travel through a wormhole, emerging elsewhere in the universe or even in a parallel reality. This idea aligns with the holographic principle, which proposes that all the information about what falls into a black hole could be encoded on its event horizon. Wormholes might serve as the mechanism by which this information is preserved and transferred. While this theory remains speculative, it offers a promising way to reconcile the laws of quantum mechanics with the behavior of black holes. The possibility that wormholes could safeguard information challenges our understanding of space, time, and the very fabric of reality. As we continue to unravel this cosmic puzzle, wormholes may prove to be more than just shortcuts through space. They could be the guardians of the universe's secrets. Next, we'll dive into how wormholes might challenge the cosmic censorship conjecture, another cornerstone of black hole physics. Turning our attention to another cornerstone of black hole physics, let's explore the cosmic censorship conjecture and how wormholes might shake up this long-standing idea. Proposed by physicist Roger Penrose, the cosmic censorship conjecture suggests that the singularities inside black holes, points where gravity becomes infinite, are always hidden behind an event horizon. This censorship ensures that the extreme conditions at the singularity don't disrupt the predictability of the universe outside the black hole. Essentially, it's nature's way of keeping the most chaotic elements of space-time tucked away. But what if wormholes could challenge this idea? If wormholes exist and connect different regions of space-time, they might create pathways that bypass the event horizon, effectively exposing the singularity. This could mean that the chaotic effects of a singularity might not stay hidden after all. Such a scenario would have profound implications for our understanding of the universe's predictability. If singularities can influence the outside universe through wormholes, the laws of physics as we know them might need a major rethink. While this theory remains speculative, it opens up a fascinating debate about the nature of black holes, wormholes, and the very fabric of reality. Next, we'll take a closer look at how wormholes might exist at the Planck scale, the tiniest possible level of space-time, and what that could mean for our understanding of quantum gravity. Shifting our focus to the smallest possible level of space-time, let's dive into the intriguing idea that wormholes might exist at the Planck scale. The Planck scale is the tiniest measurable unit of length in the universe, roughly a trillionth of a trillionth the size of an atom. At this incredibly minuscule scale, the fabric of space-time is thought to be a seething, chaotic foam, constantly bubbling with fluctuations. It's here, in this quantum foam, that microscopic wormholes might spontaneously form and disappear in the blink of an eye. These fleeting structures could be the building blocks of space-time itself, offering a glimpse into the deepest mysteries of quantum gravity. However, observing such phenomena presents a monumental challenge. The Planck scale is far beyond the reach of current technology, with distances so small and timescales so brief that detecting them seems almost impossible. Yet, theoretical physicists speculate that if wormholes do exist at this level, they could help bridge the gap between quantum mechanics and general relativity, two of the most successful but incompatible theories in physics. By studying these tiny wormholes, we might uncover clues about how gravity operates at the quantum level, potentially paving the way for a unified theory of everything. While this remains a speculative frontier, it's a tantalizing reminder of how much we still have to learn about the universe's most fundamental workings. Next, we'll explore how wormholes might impact our understanding of time itself, particularly the arrow of time and the possibility of reversing its flow. Turning our attention to the flow of time, let's explore how wormholes might influence the arrow of time, the concept that time moves in a single direction from past to future. Normally, we experience time as a one-way street. Events happen in sequence, and we can't undo them. But wormholes could challenge this idea, potentially allowing for time travel or even reversing the direction of time. One way this could happen is through the creation of closed time-like curves, hypothetical paths through space-time that loop back on themselves. Imagine traveling along such a curve. You could end up back at the same moment you started, creating a loop in time. This raises fascinating questions about causality. For instance, could you change the past? And if so, how would that affect the future? These ideas aren't just science fiction. They're grounded in the mathematics of general relativity. However, such scenarios often lead to paradoxes, like the famous grandfather paradox, where traveling back in time to prevent your own birth creates a logical contradiction. While these paradoxes make time travel seem impossible, some physicists speculate that wormholes could provide a way around them. By threading a wormhole with exotic matter, it might be possible to stabilize a closed time-like curve without breaking the laws of physics. This is still speculative, but it opens up a realm of possibilities for understanding how time works on a cosmic scale. Whether or not wormholes can truly reverse the arrow of time, they remind us that the nature of time itself is far more mysterious than we often assume. Next, we'll delve into how wormholes might connect different universes within the multiverse landscape. Shifting our perspective to the vastness of existence, let's explore how wormholes might serve as gateways to different universes within the multiverse landscape. The multiverse theory suggests that our universe is just one of countless others, each with its own unique laws of physics and realities. Imagine wormholes acting as bridges between these universes, allowing travel or communication across realms that would otherwise be entirely inaccessible. This idea isn't just speculative, it's rooted in the mathematics of string theory, which proposes that higher dimensional spaces could host these alternate universes. If wormholes do connect different universes, they could offer a way to test the multiverse theory, something that's otherwise nearly impossible to prove. For example, detecting strange particles or energy signatures passing through a wormhole might hint at the existence of another universe, but the implications go beyond just exploration. If wormholes link universes, they could provide insights into the nature of reality itself. Are these universes completely separate, or do they influence one another? Could information or even matter flow between them? These questions challenge our understanding of cosmology and push the boundaries of theoretical physics. While the idea of multiverse connecting wormholes remains unproven, it opens up thrilling possibilities for the future of science, blending the mysteries of wormholes with the enigma of the multiverse. Up next, we'll examine how wormholes might fit into the Brane-world scenario, where higher dimensional spaces play a key role in our understanding of the universe. Now, let's step into the intriguing world of the Brane-world scenario, where wormholes might play a fascinating role in connecting different branes, essentially membranes, in higher dimensional space. Picture our universe not as a standalone three-dimensional space, but as a brane floating within a higher dimensional bulk. In this model, other branes could exist parallel to ours, each potentially hosting its own universe. Wormholes in this context could act as tunnels linking these branes, allowing for interactions that defy our conventional understanding of space and time. This idea isn't just a flight of fancy, it's grounded in theories like string theory, which suggests that extra dimensions beyond the familiar three could be the key to unifying the forces of nature. If wormholes connect branes, they could offer a way to test these theories by detecting gravitational effects or particle interactions that hint at the presence of hidden dimensions. For example, gravity might leak between branes, explaining why it's so much weaker than other fundamental forces. Additionally, particle collisions in high-energy experiments, like those conducted at the Large Hadron Collider, might produce signals of brain-to-brain interactions mediated by wormholes. The implications are profound. If wormholes link branes, they could revolutionize our understanding of gravity, particle physics, and the very fabric of the cosmos. This scenario also raises questions about the nature of these connections. Could matter or energy travel between branes, or is the interaction more subtle, perhaps limited to gravitational waves or quantum effects? While the Brane-world scenario remains speculative, it offers a compelling framework for exploring the mysteries of higher dimensions and the role wormholes might play in shaping the universe or multiverse. Up next, we'll delve into the holographic universe theory, where wormholes might fit into a radically different picture of reality. Turning our attention to the holographic universe theory, we enter a realm where reality might be more like a projection than we ever imagined. This theory suggests that our three-dimensional universe could be a holographic image encoded on a two-dimensional surface, much like how a hologram creates a 3D illusion from flat data. If this is true, then wormholes might serve as critical bridges within this cosmic hologram, connecting different points of encoded information across the lower dimensional surface. Imagine the universe as a vast, intricate movie playing on a screen. Wormholes in this analogy could be the threads stitching together scenes from different parts of the film, ensuring continuity and coherence. This idea isn't just philosophically fascinating, it has deep implications for physics. If the universe is holographic, then everything we perceive, from galaxies to particles, could be manifestations of data stored on this two-dimensional boundary. Wormholes might enable the transfer of this information, acting as cosmic conduits that maintain the integrity of the hologram. For instance, a wormhole could allow information to travel instantaneously across vast distances, bypassing the usual constraints of space and time. This could explain phenomena like entanglement in quantum mechanics, where particles separated by light years seem to communicate instantly. The holographic principle also raises questions about the nature of reality itself. Are we living in a universe that's fundamentally two-dimensional, with our three-dimensional experience merely an illusion? If so, wormholes might be the key to understanding how this illusion is maintained. They could be the mechanisms that translate lower dimensional data into the rich, complex reality we observe. While this theory remains speculative, it offers a bold new perspective on the cosmos, challenging us to rethink the very fabric of existence. As we explore further, we'll uncover how wormholes might fit into another intriguing framework, the null energy condition and what it means for their stability. Now, let's shift our focus to the null energy condition and its role in the stability of wormholes. The null energy condition is a fundamental principle in physics that states that the energy density in a region of space cannot be negative. In simpler terms, it's a rule that ensures the universe doesn't break down into chaos by allowing energy to behave in unpredictable ways. But when it comes to wormholes, this condition becomes a bit of a puzzle. For a wormhole to remain open and traversable, it requires something called exotic matter, a type of matter with negative energy density. This exotic matter would essentially counteract the natural tendency of a wormhole to collapse under its own gravitational pull. However, here's the catch: exotic matter violates the null energy condition. It's like trying to build a bridge that defies the laws of physics holding it together. This violation raises significant questions. If the null energy condition is violated, what does that mean for the stability of space-time itself? Could wormholes exist only in regions where these conditions are bent? The answer isn't straightforward, but it's fascinating to consider. Some theories suggest that quantum effects might allow for temporary violations of this condition, making wormholes possible on a microscopic scale, even if only for a fleeting moment. The implications of this are profound. If exotic matter can exist even briefly, it opens the door to the possibility of stable wormholes. This would not only revolutionize our understanding of space and time, but also provide a potential pathway for interstellar travel. Yet the challenge remains: how do we reconcile the existence of exotic matter with the fundamental laws of physics? This is where the null energy condition becomes a critical piece of the puzzle, forcing us to rethink the boundaries of what's possible in the cosmos. As we explore further, we'll delve into another intriguing idea: the weak gravity conjecture and how it might constrain the existence of wormholes, adding yet another layer to this complex and captivating discussion. Turning our attention to another compelling idea, let's examine the weak gravity conjecture and its potential impact on wormholes. The weak gravity conjecture is a theoretical proposal that suggests gravity is, in some sense, the weakest force in nature. It implies that gravity cannot become arbitrarily strong compared to other fundamental forces, such as electromagnetism. This conjecture has fascinating implications for wormholes. If gravity is inherently weak, it raises questions about whether wormholes could sustain the enormous gravitational forces required to keep them open. For a wormhole to be stable, it needs to counteract the intense gravitational pull that would otherwise cause it to collapse. But if gravity is constrained by this conjecture, the existence of traversable wormholes becomes even more uncertain. Some physicists argue that the weak gravity conjecture might impose strict limits on the kinds of wormholes that could exist. For example, it could mean that only microscopic or extremely short-lived wormholes are possible, as larger ones would require gravitational strengths that violate the conjecture. This ties directly into the broader challenges of quantum gravity and string theory, which aim to reconcile the behavior of gravity with the principles of quantum mechanics. In string theory, for instance, the weak gravity conjecture is thought to play a key role in determining the properties of higher dimensional spaces and objects like wormholes. It suggests that the framework of string theory might naturally prevent the formation of large, stable wormholes, aligning with the conjecture's limits on gravity's strength. This idea opens up a new layer of complexity in our understanding of wormholes. It forces us to consider not just the exotic matter required to keep them open, but also the fundamental constraints on gravity itself. Could wormholes exist within the boundaries set by the weak gravity conjecture, or does this rule them out entirely? The answer remains elusive, but it's a question that continues to drive research in theoretical physics. As we explore further, we'll look at another intriguing puzzle, the firewall paradox, and how wormholes might offer a solution, adding yet another dimension to this fascinating discussion. Now, let's shift our focus to one of the most puzzling ideas in modern physics, the firewall paradox, and how wormholes might offer a solution. The firewall paradox arises from a conflict between two fundamental theories, quantum mechanics and general relativity. According to quantum mechanics, information is never lost, but general relativity predicts that if you fall into a black hole, you would smoothly pass through its event horizon, experiencing nothing unusual at first. The paradox begins when we consider what happens to an observer falling into a black hole. If quantum mechanics is correct and information is preserved, then a fiery firewall of high-energy particles should exist at the event horizon. This firewall would incinerate anything crossing it, completely contradicting the smooth experience predicted by general relativity. This contradiction has left physicists struggling to reconcile these two theories. Here's where wormholes enter the picture. Some researchers propose that wormholes could provide a way out of this paradox. The idea is that instead of encountering a firewall, an observer falling into a black hole might be redirected through a wormhole, preserving the information and avoiding the destructive energy barrier. This would mean that wormholes act as bridges, allowing information to escape black holes without violating the principles of quantum mechanics. The implications of this theory are profound. If wormholes can resolve the firewall paradox, they might also help us understand how information is preserved in the universe. It suggests that wormholes are not just cosmic shortcuts but essential components of the fabric of space-time, playing a critical role in maintaining the laws of physics as we know them. As we continue to explore the mysteries of black holes and wormholes, this theory opens up new possibilities for understanding the universe's most extreme environments. Next, we'll delve deeper into the connection between wormholes and quantum entanglement, uncovering even more ways these cosmic structures might shape our understanding of reality. Building on our exploration of wormholes and their role in resolving the firewall paradox, let's dive into another fascinating idea that connects the dots between quantum mechanics and general relativity, the ER=EPR conjecture. This theory, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a profound link between wormholes known as Einstein-Rosen bridges and quantum entanglement, often referred to as EPR correlations after Einstein, Podolsky, and Rosen. At its core, the ER=EPR conjecture proposes that entangled particles might be connected by microscopic wormholes. In other words, the strange, instantaneous connection between entangled particles could be explained by these tiny, hypothetical tunnels through space-time. This idea bridges the gap between the quantum world, where particles can influence each other across vast distances, and the cosmic scale, where wormholes could potentially connect distant regions of the universe. What makes this conjecture so groundbreaking is its potential to unify two seemingly incompatible theories, quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the large-scale structure of space-time. By suggesting that wormholes and entanglement are two sides of the same coin, this theory offers a way to reconcile these two pillars of modern physics. One of the key implications of the ER=EPR conjecture is that it could provide a new framework for understanding the nature of space-time itself. If entangled particles are indeed linked by wormholes, it suggests that space-time might be more deeply interconnected than we previously thought. This could even hint at a holographic universe where the information about everything in our three-dimensional reality is encoded on a two-dimensional surface. As we continue to explore this idea, it raises exciting questions about the fundamental nature of reality. Could wormholes be the hidden threads weaving together the quantum and cosmic realms? And if so, what does this mean for our understanding of the universe? Looking ahead, we'll explore another intriguing theory, the connection between wormholes and the information loss paradox, and how these cosmic structures might preserve the integrity of quantum information. Shifting our focus to another puzzle in the cosmos, let's explore how wormholes might hold the key to solving the information loss paradox. This paradox revolves around the question of what happens to information when matter falls into a black hole. According to classical physics, once something crosses a black hole's event horizon, it's gone forever, including the information about its properties. This idea, however, clashes with the principles of quantum mechanics, which state that information can never be truly destroyed. Here's where wormholes come into play. One proposed solution to the information loss paradox is that wormholes could act as hidden pathways, allowing information to escape from black holes. Instead of being lost forever, the information might travel through these hypothetical tunnels and reappear elsewhere in the universe. This idea suggests that black holes aren't the ultimate endpoints we once thought they were, but rather gateways to a more interconnected cosmos. The concept hinges on the idea that wormholes could connect the interior of a black hole to another part of space-time, possibly even to a white hole, the theoretical opposite of a black hole. In this scenario, the information swallowed by the black hole wouldn't vanish but instead be transported through the wormhole, preserving the integrity of quantum information. This theory doesn't just solve the information loss paradox, it also offers a deeper understanding of how space-time operates at its most fundamental levels. If wormholes can indeed preserve information, it implies that the universe has mechanisms in place to maintain the coherence of physical laws, even in the most extreme environments. As we consider this idea, it's worth noting that it's still highly speculative, and much work remains to be done to test its validity. However, if proven true, it could revolutionize our understanding of black holes, wormholes, and the very fabric of reality. Next, we'll turn our attention to the quantum foam, a concept that suggests space-time might be teeming with microscopic wormholes, offering yet another layer to this cosmic mystery. Now, let's zoom into the tiniest scales of the universe, where the fabric of space-time itself becomes a bubbling sea of activity known as the quantum foam. This chaotic, frothy landscape is thought to exist at the Planck scale, where the laws of quantum mechanics and gravity collide. Here, space-time isn't smooth and continuous as we perceive it on larger scales. It's a dynamic, ever-shifting mess of fluctuations. Within this quantum foam, microscopic wormholes could be constantly forming and dissolving, popping in and out of existence in fractions of a second. These tiny tunnels might not be the grand cosmic shortcuts we often imagine, but they could still play a crucial role in shaping the structure of space-time. The idea is that these ephemeral wormholes could serve as the building blocks of the universe, influencing the way particles interact and even altering the flow of time itself. At such infinitesimal scales, the distinction between past, present, and future might blur, opening the door to fascinating possibilities about the nature of reality. One implication of the quantum foam is that space-time might not be as rigid as it seems. Instead, it could be a flexible, interconnected web of wormholes constantly remolding itself. This challenges our classical understanding of space and time, suggesting that the universe is far more dynamic and interconnected than we've ever imagined. While this concept remains speculative, it offers a tantalizing glimpse into the deepest layers of reality. If microscopic wormholes are indeed part of the quantum foam, they could hold the key to unifying quantum mechanics and general relativity, a puzzle that has eluded scientists for decades. Next, we'll explore how remnants of the Big Bang might hold clues to the existence of wormholes, taking us back to the very beginning of the cosmos. Turning our gaze to the aftermath of the Big Bang, the cosmic microwave background offers an extraordinary window into the early universe. This faint glow, often referred to as the afterglow of the Big Bang, carries imprints of the universe's infancy, revealing clues about its structure and evolution. But could it also bear traces of wormholes hidden within its subtle patterns? The cosmic microwave background is like a cosmic photograph, capturing the universe as it was just 380,000 years after the Big Bang. Tiny fluctuations in this background radiation tell the story of density variations in the early universe, which eventually seeded the formation of galaxies and cosmic structures. Yet, some scientists speculate that these fluctuations could also harbor anomalies, subtle irregularities that might hint at the presence of wormholes. If wormholes existed in the early universe, they could have left distinctive signatures in the cosmic microwave background. For instance, their gravitational effects might have caused deviations in the distribution of temperature and density, creating pockets of asymmetry or unusual patterns. Detecting these anomalies could provide indirect evidence of wormholes, offering a glimpse into their role in shaping the cosmos. The challenge lies in distinguishing these wormhole signatures from other cosmic phenomena. Researchers would need to sift through vast amounts of data, looking for patterns that defy conventional explanations. Advanced simulations and machine learning techniques are already aiding this search, helping scientists identify potential markers of wormholes in the cosmic microwave background. If successful, this line of inquiry could revolutionize our understanding of both wormholes and the early universe. It would not only confirm the existence of these cosmic tunnels, but also shed light on their influence during the universe's formative moments. The cosmic microwave background, already a treasure trove of cosmological insights, might hold the key to unlocking one of spacetime's greatest mysteries. Next, we'll explore the intriguing idea that wormholes could be linked to the enigmatic substance known as dark matter, delving into how these two cosmic puzzles might intersect. Moving into another fascinating realm of speculation, let's consider the intriguing possibility that wormholes and dark matter might be deeply connected. Dark matter, that mysterious and invisible substance that makes up a significant portion of the universe's mass, has long puzzled scientists. While it doesn't interact with light or ordinary matter, its gravitational effects are undeniable, shaping galaxies and cosmic structures. But could wormholes be influencing or even interacting with dark matter in ways we've yet to uncover? One theory suggests that wormholes could affect the distribution of dark matter in the universe. If wormholes exist, their gravitational pull might subtly alter the way dark matter clumps together, creating patterns or anomalies in its distribution. These effects could be particularly noticeable in regions where dark matter is concentrated, such as galaxy clusters or the halos surrounding galaxies. By studying these patterns, scientists might find indirect evidence of wormholes, linking two of the cosmos's greatest mysteries. Another angle to explore is whether wormholes themselves could be composed of or influenced by dark matter. Given that dark matter exerts gravitational forces without emitting light, it's possible that it could play a role in stabilizing wormholes, perhaps even providing the exotic matter needed to keep them open. This idea, while speculative, opens up new avenues for research into the nature of both wormholes and dark matter, suggesting that solving one mystery could shed light on the other. The challenge, as always, lies in detecting these subtle interactions. Dark matter is already difficult to observe directly, and its connection to wormholes would require even more sophisticated methods of investigation. Advanced simulations and observational techniques are being developed to probe these possibilities, offering hope that future discoveries might reveal the hidden ties between these cosmic enigmas. As we continue to unravel the mysteries of the universe, the potential connection between wormholes and dark matter stands as a tantalizing puzzle. Exploring this idea not only deepens our understanding of these phenomena, but also highlights the intricate and interconnected nature of the cosmos. Up next, we'll revisit the black hole information paradox and explore how wormholes might offer a solution to this enduring cosmic conundrum. Shifting our focus to one of the most perplexing puzzles in modern physics, let's revisit the black hole information paradox and explore how wormholes might hold the key to resolving it. The paradox arises from a fundamental conflict between quantum mechanics and general relativity. According to quantum theory, information about the universe must always be preserved. However, when matter falls into a black hole, it appears to be lost forever, seemingly violating this principle. This contradiction has baffled scientists for decades, but wormholes might offer a way out. One compelling idea is that information swallowed by a black hole isn't truly lost but is instead transferred through a wormhole. In this scenario, the information could escape via a connection to another point in space-time, preserving it in line with quantum mechanics. This concept aligns with the idea that wormholes could serve as bridges, allowing information to traverse from one location to another without being destroyed. It's a theory that not only resolves the paradox but also ties together two of the universe's most fascinating phenomena. Another angle to consider is the role of Hawking radiation, the process by which black holes emit energy and slowly evaporate. Some physicists propose that the information carried by Hawking radiation might be linked to wormholes. If wormholes exist within or connected to black holes, they could act as conduits, ensuring that information is encoded in the radiation rather than lost forever. This would provide a mechanism for information preservation while maintaining the integrity of quantum laws. The challenge, however, lies in testing these ideas. Detecting wormholes or observing their potential role in black hole dynamics would require breakthroughs in observational technology and theoretical understanding. Current models and simulations are paving the way, but definitive proof remains elusive. Still, the possibility that wormholes could solve the information paradox is a thrilling prospect, offering a glimpse into the deeper workings of the cosmos. As we delve deeper into these theories, it becomes clear that wormholes might not just be shortcuts through space-time, but also essential tools for preserving the universe's fundamental information. Up next, we'll explore the holographic entropy bound and how it might constrain the existence of wormholes, adding another layer to this cosmic puzzle. Now, let's turn our attention to the holographic entropy bound, a concept that could have profound implications for our understanding of wormholes and the universe itself. Proposed by physicist Gerard T. Hooft and later expanded upon by Leonard Susskind, the holographic entropy bound suggests that the maximum amount of information contained within a region of space is proportional to its surface area, not its volume. This idea, rooted in the holographic principle, fundamentally challenges our traditional notions of space, information, and reality. How does this relate to wormholes? Well, if wormholes are shortcuts or bridges through space-time, their existence might be constrained by this very bound. The holographic entropy bound implies that the information content of the universe is finite and tied to its boundaries. Wormholes, as structures that potentially connect distant points in space-time, could serve as conduits for this information. However, if the entropy or information within a region of space is limited by its surface area, wormholes might not be able to carry more information than the space they connect allows. This places a natural limit on their size and function, raising questions about how they could operate without violating the bound. It's a fascinating intersection of quantum mechanics, gravity, and information theory that could reshape our understanding of cosmic structures. One intriguing possibility is that wormholes themselves could be encoded on the holographic boundary of the universe. If the universe is like a hologram, with all its information projected from a lower dimensional surface, wormholes might be emergent features of this projection. This would mean that their existence and properties are determined by the information encoded on the boundary, rather than being independent structures within space-time. Such a view aligns with the idea that wormholes are not just physical tunnels but manifestations of deeper, holographic principles governing the cosmos. The implications for the universe's information content are equally profound. If wormholes are constrained by the holographic entropy bound, they could play a role in how information is distributed and preserved across the universe. This ties back to earlier theories we've explored, such as the black hole information paradox and the role of wormholes in preserving quantum information. The holographic entropy bound adds another layer to these puzzles, suggesting that the universe's information capacity is not only finite but intricately linked to its fundamental structure. As we continue to explore the mysteries of wormholes, the holographic entropy bound serves as a reminder that our understanding of the cosmos is still evolving. It challenges us to think beyond traditional physics and consider how the universe might be fundamentally encoded in ways we're only beginning to grasp. Up next, we'll delve into the no-hair theorem and how wormholes might challenge this long-standing principle, revealing even more about the nature of space, time, and information. Moving forward, let's explore how wormholes might challenge one of the most intriguing principles in physics, the no-hair theorem. Proposed by physicist John Wheeler, the no-hair theorem suggests that black holes can be fully described by just three properties: their mass, electric charge, and angular momentum. This means that no matter how complex an object is before it falls into a black hole, all other details are seemingly lost, leaving behind a simple, bald description. It's a concept that has fascinated physicists for decades, but wormholes might just throw a wrench into this elegant idea. If wormholes exist, they could defy the no-hair theorem by possessing properties that go beyond mass, charge, and angular momentum. Unlike black holes, which are thought to erase nearly all information about what falls into them, wormholes might retain additional details about the objects or information passing through them. This would mean that wormholes could have a kind of hair, unique features or hidden parameters that make them far more complex than black holes. Such a possibility could fundamentally reshape our understanding of how information is preserved in the universe. One way to think about this is through the lens of quantum mechanics. In quantum theory, information is never truly lost. It's just transformed or encoded in different ways. If wormholes are linked to quantum entanglement or other quantum phenomena, they might carry information in ways that black holes cannot. This could challenge the no-hair theorem by showing that certain cosmic structures, like wormholes, can retain and transmit information in ways we're only beginning to understand. Additionally, wormholes might not just be tunnels through space-time but could have intricate internal structures or dynamics that set them apart. For example, they could contain exotic matter or fields that give them unique properties, effectively giving them hair that black holes lack. This could open up new possibilities for studying the universe, as wormholes might serve as windows into deeper aspects of physics that black holes alone cannot reveal. The implications of this are profound. If wormholes do possess unique properties beyond the no-hair theorem, it could mean that our understanding of black holes is incomplete. It might also suggest that the universe has more complex structures and mechanisms for preserving information than we've ever imagined. As we continue to unravel the mysteries of wormholes, the no-hair theorem remains a fascinating benchmark, one that wormholes might just push us to rethink. Next, we'll examine how the cosmological constant might influence the stability of wormholes, shedding light on another piece of the cosmic puzzle. Now, let's turn our attention to another fascinating aspect of wormhole theory, the cosmological constant. This mysterious force, first introduced by Albert Einstein, plays a crucial role in shaping the fabric of the universe. It's often associated with the acceleration of the universe's expansion, but its influence might extend even further, potentially impacting the stability and structure of wormholes. The cosmological constant represents a form of energy that permeates all of space, acting as a kind of anti-gravity force. While it's most famously linked to the accelerated expansion of the universe, some physicists speculate that it could also affect the behavior of wormholes. Specifically, this constant might counteract the forces that would otherwise cause a wormhole to collapse, helping to keep it open and traversable. One way to think about this is through the lens of general relativity. According to Einstein's equations, the cosmological constant introduces a repulsive force that counteracts gravity. In the context of wormholes, this repulsion could balance the intense gravitational pull that tends to close these cosmic tunnels. Without such a counterforce, wormholes would likely collapse almost instantly, making them impossible to traverse. But with the cosmological constant in play, there's a possibility that wormholes could remain stable, at least long enough for something or someone to pass through. However, the cosmological constant isn't just about stability. It might also influence the overall structure of wormholes, shaping their size, shape, and even the way they connect different regions of space-time. For example, if the cosmological constant is strong enough, it could create conditions that allow wormholes to exist on a much larger scale, potentially making them viable for interstellar travel. On the other hand, if it's too weak, wormholes might remain microscopic or unstable, limiting their practical use. The implications of this are profound. If the cosmological constant does play a role in stabilizing wormholes, it could mean that this mysterious force is not just shaping the universe on a grand scale, but also influencing the most intricate cosmic structures. This would deepen our understanding of both wormholes and the cosmological constant itself, potentially revealing new connections between the large-scale behavior of the universe and the microscopic details of space-time. As we continue to explore these ideas, the cosmological constant remains a key piece of the puzzle, offering insights into how wormholes might exist and function within the broader framework of the universe. Next, we'll delve into the concept of quantum gravity and how it might be intertwined with the nature of wormholes. Shifting our focus to the intersection of quantum mechanics and general relativity, we find wormholes playing a pivotal role in the ongoing quest to unify these two fundamental theories. Quantum gravity, a theoretical framework aimed at merging these domains, often considers wormholes as essential components. Unlike the large-scale structures governed by general relativity, wormholes at the quantum level are envisioned as tiny, ephemeral tunnels woven into the very fabric of space-time. One of the central challenges in physics is reconciling the probabilistic nature of quantum mechanics with the deterministic framework of general relativity. Wormholes could offer a unique bridge between these seemingly incompatible theories. In quantum gravity models, these cosmic shortcuts are not static entities but dynamic, fluctuating structures that emerge and vanish on the smallest scales. This aligns with the quantum principle that particles can pop in and out of existence, suggesting that wormholes might do the same. A particularly intriguing idea is that wormholes could act as conduits for quantum information, linking distant regions of space-time in ways that defy classical physics. This concept ties into the ER=EPR conjecture, which proposes that entangled particles might be connected by microscopic wormholes. If true, it would mean that quantum entanglement and wormholes are two sides of the same coin, offering a profound connection between quantum mechanics and the geometry of space-time. Furthermore, wormholes in quantum gravity theories could help resolve some of the most puzzling paradoxes in modern physics, such as the black hole information paradox. By providing pathways for information to escape black holes, these tiny tunnels might preserve the integrity of quantum mechanics while still respecting the principles of general relativity. This dual role underscores their potential as a unifying element in the search for a theory of everything. As we delve deeper into this connection, it becomes clear that wormholes are more than just speculative shortcuts through space-time. They could be the missing link that ties together the quantum and cosmic realms. Their presence in quantum gravity theories not only deepens our understanding of the universe, but also brings us closer to solving one of the greatest mysteries in physics. Next, we'll explore how wormholes might fit into the holographic dark energy model, further expanding their role in shaping the cosmos. Turning our attention to the holographic dark energy model, we find yet another fascinating layer to the wormhole mystery. This theory suggests that the universe's accelerating expansion can be explained by dark energy, a mysterious force permeating space. But what if wormholes have a hidden role in this cosmic phenomenon? The holographic dark energy model proposes that the universe behaves like a hologram, where information about its contents is encoded on a lower dimensional surface. Intriguingly, wormholes might serve as the threads stitching together this holographic reality, connecting distant regions of space in ways that influence the universe's expansion. One of the key ideas here is that wormholes could modulate the effects of dark energy, acting as conduits for its distribution across the cosmos. If dark energy is the force driving the universe's acceleration, wormholes might channel its influence, shaping how galaxies and other structures expand over time. This interplay between wormholes and dark energy could help explain why the universe's expansion appears to be speeding up, a puzzle that continues to baffle scientists. Moreover, the holographic dark energy model suggests that wormholes might not just be passive players but active participants in the universe's evolution. By bridging different regions of space, they could create a network of energy flows that sustain the holographic framework. This would mean that wormholes are not only cosmic shortcuts but also vital components in maintaining the universe's balance and structure. As we consider these possibilities, it becomes clear that wormholes could hold the key to understanding some of the most profound mysteries of our universe. From their role in bridging quantum mechanics and general relativity to their potential influence on dark energy and cosmic expansion, wormholes continue to challenge and inspire our understanding of reality. Next, we'll revisit the information paradox and explore how wormholes might offer a definitive solution to this enduring puzzle in physics. Building on this cosmic puzzle, let's revisit the information paradox, a long-standing mystery in physics that challenges our understanding of black holes and information conservation. The paradox arises because, according to quantum mechanics, information cannot be destroyed. Yet, black holes seem to devour matter and radiation completely, leaving no trace of the information they once contained. This contradiction has puzzled scientists for decades, and wormholes might just hold the key to resolving it. One intriguing idea is that wormholes could act as hidden channels, preserving quantum information that seems lost in black holes. Instead of information being destroyed, it might travel through a wormhole, emerging elsewhere in the universe or even in a parallel dimension. This would mean that black holes aren't the cosmic dead ends they appear to be, but rather gateways to a vast, interconnected network of space-time. Another possibility is that wormholes could create microscopic bridges between particles entangled across space and time. This aligns with the ER=EPR conjecture, which suggests that entangled particles are connected by tiny wormholes. If true, this could explain how information escapes black holes, flowing through these hidden tunnels rather than being annihilated. The implications of this theory are profound. If wormholes can preserve quantum information, they could help reconcile the clash between quantum mechanics and general relativity, two foundational theories of physics that currently don't align. This would not only solve the information paradox, but also bring us closer to a unified understanding of the universe. As we explore these ideas, it's clear that wormholes are more than just cosmic shortcuts or time travel routes. They might be the missing link in our quest to understand the true nature of reality. Next, we'll examine the cosmic censorship hypothesis and how wormholes might challenge our assumptions about the predictability of the universe. Turning our attention to another fascinating idea, let's explore the cosmic censorship hypothesis and how wormholes might shake up this long-standing principle. The cosmic censorship hypothesis, proposed by physicist Roger Penrose, suggests that the universe has a built-in mechanism to prevent singularities, infinitely dense points in space-time, from being exposed. In other words, nature hides these singularities behind event horizons, like those of black holes, to ensure the universe remains predictable and governed by the laws of physics as we know them. But what if wormholes could challenge this idea? If wormholes exist, and if they could expose singularities, this could throw a wrench into the predictability of the universe. Imagine a scenario where a wormhole connects two points in space-time, bypassing the usual cosmic censorship. This could mean that singularities, which are normally hidden, might become visible or accessible, potentially disrupting the laws of physics as we understand them. This raises profound questions. If singularities are no longer hidden, could we still rely on our current understanding of space-time? Would the universe become a more chaotic and unpredictable place? Some physicists argue that wormholes might even create scenarios where the laws of physics break down entirely, challenging the very foundations of our scientific knowledge. On the flip side, if wormholes do expose singularities, they could also open up new possibilities for exploration and discovery. Understanding these exposed singularities might lead us to deeper insights into the nature of space, time, and the universe itself. It's a double-edged sword. While it could disrupt our current understanding, it could also pave the way for groundbreaking revelations. As we consider these implications, it's clear that wormholes have the potential to not only challenge the cosmic censorship hypothesis, but also reshape our understanding of the universe's fundamental rules. Next, we'll investigate the Planck star hypothesis and how it might relate to wormholes, diving into the idea that collapsing stars could form Planck-sized wormholes. Shifting our focus to another intriguing possibility, let's dive into the Planck star hypothesis and its fascinating connection to wormholes. Proposed as a potential resolution to the black hole information paradox, the Planck star hypothesis suggests that instead of forming a singularity at their center, collapsing stars might reach a point where quantum gravity effects prevent further collapse. At this stage, the star would stabilize as an object no larger than the Planck length, the smallest possible scale in the universe. Now, here's where wormholes come into play. Some physicists speculate that these Planck-sized objects could actually function as microscopic wormholes. Instead of a singularity, the core of a black hole might house a Planck star connected to a wormhole, offering a pathway to another region of space-time. This idea not only challenges our traditional understanding of black holes, but also provides a possible solution to the information paradox, as information could escape through these tiny wormholes rather than being lost forever. What makes this theory particularly exciting is its blend of quantum mechanics and general relativity. Planck stars and their associated wormholes could represent a bridge between these two fundamental yet seemingly incompatible frameworks. If true, this would be a monumental leap forward in our understanding of the universe's most extreme environments. However, the Planck star hypothesis is still highly speculative. Detecting or proving the existence of such tiny structures is beyond our current technological capabilities. Yet, the idea sparks curiosity and invites us to rethink the nature of black holes and the role of wormholes in the cosmos. Could these Planck-sized wormholes be the key to unlocking the mysteries of quantum gravity? As we ponder this possibility, it's clear that the Planck star hypothesis offers a compelling new perspective on the relationship between collapsing stars, black holes, and wormholes. Next, we'll revisit the holographic principle and explore how wormholes might fit into this framework, examining the idea that the universe itself could be a projection from a lower dimensional surface. Turning our attention back to the holographic principle, this theory offers a radical perspective on the nature of reality. At its core, the holographic principle suggests that all the information in a volume of space can be thought of as encoded on a lower dimensional boundary, much like a hologram projects a three-dimensional image from a two-dimensional surface. This idea challenges our conventional understanding of space and raises intriguing questions about the structure of the universe. Now, how do wormholes fit into this framework? Some physicists propose that wormholes could serve as connections between these lower dimensional surfaces, acting as pathways through which information flows. Imagine the universe as a vast hologram. Wormholes might be the threads stitching together different regions of this cosmic projection, enabling the transfer of information across dimensions. This idea ties back to earlier theories like the ER equals EPR conjecture, which links wormholes to quantum entanglement. Just as entangled particles share information instantaneously, wormholes might facilitate a similar exchange on a much larger scale, bridging distant parts of the universe. The holographic principle also offers an alternative explanation for the behavior of black holes and wormholes. Instead of viewing them as purely gravitational phenomena, we can think of them as manifestations of information processing on a lower dimensional surface. This perspective could help resolve long-standing puzzles in physics, such as the black hole information paradox, by suggesting that information is never truly lost but simply encoded elsewhere. While this theory is still in its infancy, it opens up exciting possibilities for understanding the universe. If the holographic principle is correct, and wormholes are indeed part of this intricate information network, it could revolutionize our view of space, time, and reality itself. As we explore these ideas, it's clear that the holographic principle and wormholes together offer a fascinating lens through which to examine the cosmos. Next, we'll delve into the black hole firewall paradox and how wormholes might provide a solution to this perplexing mystery, bringing us one step closer to unraveling the deepest secrets of the universe. Shifting our focus to the black hole firewall paradox, we encounter one of the most perplexing mysteries in modern physics. This paradox arises from a clash between quantum mechanics and general relativity. According to quantum theory, the event horizon of a black hole should be a relatively calm region of space. However, calculations based on general relativity suggest that it might instead be a searing wall of energy, a firewall that would incinerate anything falling into the black hole. This contradiction has left physicists scratching their heads for years. So where do wormholes come into the picture? Some theorists propose that wormholes could offer a way out of this dilemma. Imagine a scenario where the interior of a black hole isn't a one-way trip to destruction, but instead connects to another region of space-time via a wormhole. In this case, the firewall might never form because the information and energy falling into the black hole could escape through the wormhole, preserving the integrity of the laws of physics. This idea aligns with the holographic principle we discussed earlier. If the information about what falls into a black hole isn't lost but instead encoded elsewhere, there's no need for a firewall to scramble it. Wormholes could act as the conduits that transport this information safely, ensuring that nothing is truly destroyed. But how plausible is this solution? While it's still a highly speculative idea, it offers a compelling way to reconcile the firewall paradox with our understanding of quantum mechanics. If wormholes do exist and function as cosmic escape routes, they could prevent the formation of firewalls altogether, maintaining the harmony between quantum theory and gravity. As we continue to explore this theory, it's clear that wormholes might hold the key to solving some of the universe's most baffling puzzles. Next, we'll turn our attention to the final theory in our exploration: how wormholes could be a cornerstone in the quest for the ultimate theory of everything, tying together the threads of physics into a single, unified framework. Now, let's explore the grand finale of our journey: wormholes and their potential role in the ultimate theory of everything. For decades, physicists have been searching for a single framework that unites quantum mechanics and general relativity, two of the most successful yet fundamentally different theories in science. Quantum mechanics explains the behavior of particles at the smallest scales, while general relativity describes the force of gravity on the grand cosmic stage. But when these two theories are applied together, they clash, creating paradoxes and unanswered questions. This is where wormholes might come into play. Wormholes could serve as a bridge between these two realms of physics. Imagine them as cosmic connectors that link the quantum world to the universe's larger structure. In some theories, wormholes are seen as natural consequences of quantum gravity, the yet-to-be-discovered theory that would reconcile quantum mechanics and gravity. By studying wormholes, we might uncover clues about how these two forces interact at their most fundamental level. One intriguing possibility is that wormholes could help explain the nature of space-time itself. If space-time is woven from tiny, quantum-scale threads, wormholes might represent knots or loops in this fabric, connecting distant regions or even different universes. This idea aligns with the holographic principle, which suggests that all the information in the universe could be encoded on a lower dimensional surface, like a cosmic hologram. Wormholes could be the pathways that allow this information to flow and interact, preserving the unity of physical laws. Moreover, wormholes might hold the key to understanding the origins of the universe. Some theories propose that the Big Bang itself could have been a wormhole-like event, creating a bridge between nothingness and the cosmos we observe today. If true, wormholes wouldn't just be cosmic shortcuts, they'd be fundamental to the very fabric of existence. While these ideas are still speculative, they highlight the potential for wormholes to transform our understanding of physics. By exploring their role in quantum gravity, space-time, and the universe's beginnings, we might inch closer to the elusive theory of everything, a single, unifying framework that explains all the forces and particles in nature. As we conclude this exploration of wormholes, it's clear that these enigmatic structures are more than just science fiction. They're a gateway to some of the most profound questions in physics, offering tantalizing possibilities for understanding the universe at its deepest level. Whether they exist or remain a theoretical construct, wormholes challenge us to think bigger, bolder, and beyond the limits of our current knowledge. Thank you for joining us on this journey through 50 theories about wormholes and space-time travel. Which of these ideas fascinates you the most? Share your thoughts in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the cosmos. Until next time, keep wondering and keep exploring. As we wrap up this journey through 50 theories about wormholes and space-time travel, it's remarkable to see just how diverse and imaginative these ideas are. From Einstein's early concepts of bridges in space-time to the mind-bending possibilities of multiverses and time loops, wormholes have captured the curiosity of scientists and dreamers alike. Each theory offers a unique lens through which we can explore the mysteries of the cosmos, pushing the boundaries of what we know about space, time, and even the very fabric of reality. What makes wormholes so fascinating is their potential to revolutionize our understanding of the universe. Whether they're seen as cosmic shortcuts, gateways to parallel universes, or fundamental components of quantum gravity, they challenge us to rethink the rules of physics and our place in the cosmos. The sheer diversity of these theories highlights the endless creativity and ingenuity of human thought, proving that even the most speculative ideas can spark meaningful discoveries. As we reflect on these 50 theories, it's clear that wormholes are more than just science fiction. They're a gateway to some of the most profound questions in science. They invite us to imagine a universe where the impossible might just be possible, where the boundaries of space and time are no longer fixed, and where the mysteries of existence are waiting to be unraveled. Now it's your turn to join the conversation. Which of these theories resonated with you the most? Do you see wormholes as the key to interstellar travel, time travel, or something even more extraordinary? Share your thoughts in the comments below. We'd love to hear your perspective. And if you've enjoyed this deep dive into the mysteries of wormholes and space-time travel, don't forget to subscribe for more explorations of the cosmos. Hit the notification bell so you never miss an update, and let's keep wondering, exploring, and uncovering the secrets of the universe together. Until next time, keep looking up.